Okay, this was supposed to be in yesterday's video, but I forgot to talk about it. So it's just going to be its own video. In this video, we're going to learn how to find the volume of shapes with known cross sections. For those of you that aren't familiar, a cross section is the shape that you see when you take another shape and you cut into it, and it's the face that you see when you open it up. So for example, if I made a cut in this rectangular prism right here, and then I pulled it apart like this, then when I look at it and see the face, it'll be a square. Similarly here, if I cut like this about the contour, just perpendicular to this surface, and then when I cut it and I open it up, I'll see a circle. Okay, so when we say that we're filling a solid with a shape perpendicular to some axis, what we mean is, so for example here, from the top view looking straight down, if I say we're filling this shape with equilateral triangles perpendicular to the x-axis, that means I'm going to go ahead and here that's the base of one triangle, two triangles, three triangles, 4, 5. And so I'm going to line this up with triangles inside, and each triangle's base is going to be the height of the curve. And from the side view, what's going on is there's a triangle like here, and then like here, like this, and so on until we fill this entire shape with triangles. Now we actually have to find the volume of this thing. And so to understand how we do that, we need to take a closer look at what we're filling our solid with. So I said, and I'm just going to keep going with the equilateral triangles, that the cross section of this shape is an equilateral triangle. So what this means is if I cut into it right here and I take the side view, then I'll see an equilateral triangle. But we've actually filled the shape with triangular prisms, like something like this, where we have this base I'll call B, and this width I'll call X. And I can call this X because when we fill it with triangles, these triangles are oriented with the tips pointing towards us or out of the page. And so if we turn it like this and then we put it here, we see that this width is X. So now we've decided we're going to fill the shape with triangles of base B and width X. But to get it as accurate as possible, remember that we have to put an infinite number of triangular prisms in here. And so we have to make this length dx. And when we make this length dx, the volume of one of these triangular prisms is, using this formula, root 3 over 4 base squared dx. And then if you take a closer look here, when we orient this so that dx is along the x-axis, you'll notice that b is just the height of the curve. So I'm going to call this f of x. And all that's left is to integrate, and we're going to sum these infinite triangular prisms about this whole solid, and that's how we get the volume. These are the three most common shapes that you'll be asked to fill solids with and find the volumes of. And I've listed these formulas here, and these are all derived from the area formulas. So notice this is base squared, this square root 3 over 4 base squared. This is 1/2 pi r squared, where r is, now if this is a semicircle, then half of this is the radius. So it's f over 2 is the radius. And all of these formulas can just be boiled down to the volume is the integral from a to b of the area formula of whatever you're filling with dx. And then of course, depending on what shape you're given, you'll have to adjust these accordingly. So for example, in this case, since I've just mirrored it over the x-axis, this would become 2f of x, because that's the base here. This would become 2f of x as well, and then this would just be normal f of x. And of course, that's when filling with shapes perpendicular to the x-axis. That's when you use this in terms of x. But if you're asked to fill it with shapes perpendicular to the y-axis, kind of like this, then all you have to do is just rewrite f of x as a function of y, and then you're good to go. And for the example for this video, I'm going to do the same problem, but two ways. Once in terms of x and once in terms of y. So we're asked, consider the shape formed by root x minus x squared and the x-axis. So before anything else, let's consider that shape. So if you plot this, you'll see that root 9 minus x squared is a semicircle from -3 to +3. And we're asked to fill the shape with semicircles perpendicular to the x-axis and find the resulting volume. So right away, we're told that we're going to be filling this with semicircles, so I'm going to set out my integral to reflect that. Now we have to choose our radius, and it's important that we make a good judgment about this because if we go wrong here, then everything after this is wrong. So the entire length of a semicircle perpendicular to the x-axis will lie like this. So this length represents the diameter of the semicircle, but we want the radius. So we're going to cut this in half. And then we're going to notice that this line, as we move along the x-axis, this is just f of x. And half of that is just 1/2 f of x. So I'm going to make the substitution like so. And now all that's left is just plug in f of x and solve the integral. So now I've plugged in our function, and then I'm going to apply the square, like so. And then I'm going to bring out all the constants outside the integral, like so. And now I'm going to integrate this term by term using the power rule. The integral of 9 minus x squared is 9x minus 1/3 x cubed, and we're evaluating this from -3 to +3. And this is equal to pi over 8 times 18 minus -18, which is pi over 8 times 36, which is 9 pi over 2. That's the volume you get when you fill this shape with semicircles perpendicular to the x-axis. So I'm going to keep our answer here in mind because we're going to do the exact same problem, but with semicircles perpendicular to the y-axis this time. We know that we're filling with semicircles, so I'm going to write my integral to reflect that, like so. But now, in order to use it in this form, we have to get our function in terms of y. Okay, so I'm just going to let y equal root 9 minus x squared and then solve for y. So this is our function of y that we're going to work with to get our radius. First, we have to choose our integration bounds. So if you'll notice, last time we went from -3 to 3 because that's where the shape was bound in terms of x. But on the y-axis, it only goes from y equals 0 to y equals 3. So our integration bounds for this problem are from 0 to 3. We're first going to notice that this function, x equals square root of 9 minus y squared, represents the distance from the y-axis to the curve, like this. And since we're filling with semicircles perpendicular to the y-axis, they're going to lie all across here. So in fact, this is already our radius. So we can just go ahead and plug it in here. And then I'm just going to go ahead and solve the integral. So I'm going to begin by applying the square, like so, and then I'm going to bring out the constant. This is what we get after integrating, and we're evaluating this from 0 to 3. And so this gives us 18 minus 0, which is 18 pi over 2. And this simplifies to 9 pi. And now you'll notice that our answer when we filled it perpendicular to the y-axis is double what we got when we filled it perpendicular to the x-axis. So the reason why this happens is because remember when we filled it with semicircles perpendicular to the x-axis, this length represented the diameter of the semicircle. But when we did it with respect to the y-axis, the same length represented the radius of the circle. So we effectively filled this with twice as many semicircles as before, which is why we got twice as much volume.